Has the secret of the Hubble pressure at last been addressed? The way that the universe is growing quicker than it should, in principle, is one of the most noteworthy secrets in space research. However, presently, specialists from the universities of Bonn and St. Andrews have found something that could lead directly to the solution of this irritating galactic issue. Our Milky Way might be situated in a tremendous void, and consequently in an especially empty region of the universe. When we apply an alternative hypothesis of gravity, the inconsistency between the theoretical and really measured development pace of the universe can be made sense of substantially. Sadly, however, there is a little catch to this groundbreaking methodology. It is an obvious scientific inconsistency to the cosmological standard model, which has for quite some time been part of the basics of cosmology. Today, marked by a significant change in perspective around quite a while back, for ages, analysts of the past were convinced that the universe was an inflexible constant, developing even. A certain Albert Einstein at first clung to the possibility of a static universe so much that he added a cosmological constant to his equations, a step he later lamented as the greatest blunder of his life. And although the youthful Belgian cleric and astrophysicist Georges Lemaitre had already shown Einstein in 1927 how a mathematical model describing an expanding universe could be created from the general theory of relativity, Einstein excused this concept as a mere mathematical contrivance. However, we know that Lemaitre's discoveries had a conclusive benefit. After all, they made a prediction that could actually be observed. Specifically, it overcame any issues between the extension of the universe and the light from galaxies. If the universe is truly expanding, the other systems in space should get away from us, just as the dots drawn on an inflatable get away from one another when it is inflated. At the same time, the light from the galaxies would be extended on its way to us, and the frequencies would be stretched, causing the light that reaches our natural eye to be shifted into the red. Indeed, in the late 1920s, the American astronomer Edwin Hubble was able to demonstrate just that. His difficult assessment of many galaxies at the Mount Wilson Observatory in California showed that the light was, without a doubt, redshifted, and the expansion of the universe was practically recognizable. However, this situation was also connected to a no less revolutionary inverse end. If the universe is continually expanding, then observed in reverse, it should also have had a beginning, a small point from which everything once arose. And while that small point is now at the core of the theory of the universe's origin, in the 1990s, cosmologists realized that the universe isn't just growing, but that its pace of development is also increasing. Dark energy is believed to be the baffling main impetus behind this speed-up, a mysterious force that is expected to check the power of gravity. The secret of Hubble strain. For what reason is the universe extending quicker than it should? A principal center of the vast development puzzle. One of the key questions in this development involves the speed at which the universe is growing as described by the Hubble constant. On paper, it is shown to relate to the pace of expansion. Yet, in practice, the specific determination of this value has led scientists into a field of confounding deviations, generally known as the Hubble tension. According to the standard model, the Hubble constant should be around 67 kilometers per second per megaparsec. To put this into perspective, 1 megaparsec is around 3.26 million light-years, while 1 light-year is 9.46 trillion kilometers. In other words, this means that the speed at which the galaxies in space move away from one another increases by 67 kilometers per second for every 3.26 million light-years. That's a significant 24,400,000 kilometers per hour per megaparsec. But it may be significantly quicker. As previously mentioned, these are just the theoretical predictions. But when we determine the value of the Hubble constant using direct cosmic measurements, such as supernova gravitational lenses, variable stars, or red giants, it suddenly adds up to 73 kilometers per second per megaparsec. Again, that's 264,000 kilometers per hour per megaparsec, and hence an inconsistency of an incredible 20,000 kilometers per hour per megaparsec. But how could this fundamentally higher value be explained? Is it possible that previous studies were flawed with distorting measurement errors? Well, This was exactly the question that the James Webb Telescope addressed when it examined the data from the Hubble telescope in the course of new observations. Specifically, the research group led by Nobel-winning physicist Adam Rees of Johns Hopkins University in Baltimore focused on the data that Webb had gathered over the past 2 years. Since the capabilities of the most current space telescope ever far surpass those of its predecessor, this new data is expected to offer critical insights into this cosmic puzzle. Ancestors specialists say that it shows us the universe in HD. So, to talk thus, the specialists had the option to partake in a razor-sharp affirmation of the Hubble strain. The assessment of the largest Webb informational collection to date, which included supernova variable stars, red giants, and a class of carbon-rich monster stars, showed that the universe doesn't, in fact, act as anticipated by the hypothesis. In like manner, the general outcome this time also yielded a Hubble constant of 72.6 kilometers per second per megaparsec. As indicated by Rees, the inconsistencies between the anticipated and noticed development rates in a real sense shout that our comprehension of the universe is basically deficient in such manner. It's possible that we have, up until this point, neglected a part that gave the youthful universe a startling drive later, the Big Bang. Moreover, it could also be that dark energy is changing, for example, that it is denser or more serious today than in the prior cosmic parts. It should be noted at this point, anyway, that analysts are also examining options in contrast to the impact of dark energy. One of these is based on the thrilling thought that the Milky Way, alongside our Earth, is situated in an immense void. Is the Milky Way caught in a supervoid? To understand what this tremendous void is about, we first need to review the all-encompassing design of the universe. As is notable, stars and planetary systems are tracked down in galaxies, which, in turn, join to form galaxy clusters and then structure superclusters. For quite a while, scientists saw the largest interactive structures in the universe in such superclusters. However, then the large-scale studies showed that the superclusters are in no way, shape, or form arbitrarily distributed in space but rather organized in a network-like structure. The grid of this structure is formed by lengthy strands known as fibers, which can be a few 100 million light-years across. In the same breath, the fibers also span massive, basically matter-free bubbles, the so-called voids. And although the daily perspective of the atmosphere looks like an extravagant galactic display, some scientists expect that these holes even make up the greater part of the universe. Expressed in calculations, this means that an estimated 50 to 90% of the universe is described by a yawning bereft of matter. A review led by Sergei Marrow of the College of Bonn now suggests that the impact of the voids might lead directly to the resolution of the development puzzle. The study, done in collaboration with researchers from the College of St. Andrews in Scotland, depends on a new observation showing that the Earth is, as a matter of fact, situated in a region of space with somewhat minimal matter, similar to an air bubble heated into a cake. Thus, the density of matter around the air pocket is much higher, and gravitational forces emanate from it, pulling the galaxies inside the air pocket closer to the edge of the pit. What sounds both simple and plausible could eventually amount to just that. Consequently, the galaxies are moving away from us faster than one would expect. In this context, the deviations of the Hubble constant can thus be explained by a local underdensity, a simple explanation, but one that has a small yet vital catch. The standard model doesn't accommodate such underdensities or voids by any means, because matter and space should really be evenly distributed. They shouldn't exist at all. But how, then, can the 600 million light-years distant galaxies be explained, for instance, which were inspected by another research group and which are fleeing from us multiple times faster than the standard model of cosmology permits? Well, in this regard, Pavel Kupa, who was also involved in the void study, states that the standard model is based on a theory of the nature of gravity proposed by Einstein and that gravitational forces might act uniquely in contrast to what the creator of the theory of relativity anticipated. Specifically, the research groups at the universities of Bonn and St. Andrews used a modified theory of gravity in their virtual experience. The adjusted Newtonian dynamics, or MOND for short, was proposed by the Israeli physicist Mahim Graham nearly 40 years ago and is still considered a pariah theory today. But Mond predicts the presence of large void bubbles in space. And that is precisely the key point, because if gravity really acts as Graham expects, the issue of the Hubble strain would vanish in one fell swoop, and since the observed deviations would be due to abnormalities in the distribution of matter, there would indeed be only one constant for the expansion of the universe. On the other hand, however, this would also mean that we would need to leave the established theories of Newton and Einstein about the nature of gravity. And Coupa complains that this is precisely the considerable research obstacle. More specifically, the astrophysicist refers to the stronghold of established theories, which plays a significant role in the allocation of research funding. Approaches that test long-established ideas are often dismissed as wild or informal. This is why it's even more difficult to get funding from the relevant councils. Our board has just approved your free membership. We'd be happy if you click approval and hit subscribe now so you won't ever miss a new video from us again. We'll see you soon.